You know the periodic table, right? That giant, colorful chart from the wall of every chemistry classroom. We've all seen it. And for most of us, it's just this intimidating grid of letters and numbers we had to memorize. But what if I told you it's not a list at all? What if it's actually a map? A treasure map even. One that's filled with hidden patterns and secret rules that can predict exactly how any element in the universe will behave, just by knowing where it is on the grid. Today, we're going to learn how to read that map.
So that really brings us to the big question, doesn't it? Is this whole thing just a random jumble of elements that we've tried to organize? Or is there some deep secret logic holding it all together? The answer is a huge emphatic yes. The periodic table is governed by a set of rules that are actually surprisingly simple. And once you get them, you'll be able to look at this chart and read it like a pro. We're about to decode the secrets that explain everything from why iron rusts to why helium balloons float. Okay, so let's get into it. You might be looking at this huge table and thinking, this is going to be complicated. But it's not. Almost every single trend, every pattern you see, it all boils down to a simple battle. A constant tug of war that's happening inside every single atom between just two basic opposing forces. If you can really wrap your head around this one central conflict, I promise you the rest of the periodic table is going to snap right into focus.
So let's meet our two fighters in this atomic battle. In one corner, you've got the inward pull. This is what chemists call the effective nuclear charge, or ZFF for short. Think of it like a tiny, powerful sun at the center of the atom, the nucleus. It's packed with positive protons, and it's constantly pulling on the negatively charged electrons orbiting it. In the other corner, you've got the outward push. This is called electron shielding. You see, it's not just an empty void between the nucleus and the outermost electrons. There are other electrons in there, in lower shells. And these inner electrons basically act like bodyguards. They get in the way, creating a sort of shield that blocks the full force of the nucleus's pull from reaching those outer electrons. So it's always this epic tug-of-war, the nucleus pulling in and the inner electrons pushing out. The winner of this fight determines pretty much everything.
So, what's the first thing this atomic tug-of-war decides? Well, it determines the most basic, fundamental property of an atom, its size. The atomic radius is the first domino we need to knock over, because as we're about to see, almost everything else, how an atom reacts, how much energy it has, how it bonds to other atoms, is a direct result of just how big or how small it is.
So, what are we talking about when we say atomic radius? It sounds technical, but it's really simple. It's just the size of the atom. Specifically, it's the distance from the very center of the nucleus all the way out to the edge of the outermost shell of electrons. It's the atom's personal bubble, its physical footprint. Simple enough, right? But the way this size changes as you move around the periodic table is where things get really interesting, and it's all because of our two competing forces.
Let's start with the easy, intuitive trend. What happens when you move down a group, one of the vertical columns? Well, the atoms get bigger. And this just makes sense. Every time you move down a row on the table, you are adding a whole new layer of electrons, a new energy shell. I love the snowman analogy for this. The top of the table is the small head. Go down a row, you add a bigger ball for the torso. Go down again, you add a huge ball for the base. You're physically adding more layers, pushing the outer edge of the atom further and further out. On top of that, each new layer adds more shielding, which strengthens that outward push, making it even harder for the nucleus to hold on tight. So you get bigger. Simple.
Okay, now get ready for the one that messes with everyone's head at first. As you move from left to right across a period, a horizontal row, the atoms actually get smaller. I know, that feels totally wrong. You're adding more protons, more electrons, more stuff. Shouldn't it get bigger? Well, this is where that tug-of-war is so important. As you go across a row, yes, you're adding electrons, but they're all going into the same outer shell. You're not adding new layers like our snowman. But, and this is the critical part, for every electron you add, you are also adding one more proton to the nucleus. This makes that inward pull, the ZF, stronger and stronger and stronger. The nucleus gets more and more powerful, and it just yanks that entire electron cloud in tighter and closer to the center. The inward pull totally dominates. So, lithium on the far left of its row is actually the biggest, and neon on the far right is the smallest. It's a bit of a mind bender, but it's a perfect example of our two forces at work.
So who cares? Why does it matter if atoms get bigger or smaller? Well, this is why. We now understand the layout of the atomic map. Big atoms are in the bottom left, small atoms are in the top right. And that single fact is the key to understanding an atom's personality. Its size directly controls how it's going to behave in the real world. Specifically, how easily it will give away its electrons or how desperately it wants to steal them from somebody else. This is chemistry, right here.
Let's first talk about what it takes to actually remove an electron from an atom. This property has a name, ionization energy. It is literally the amount of energy you have to spend to grab an atom's outermost electron and pull it away completely. A really helpful way to think about it is as the price tag for stealing that electron. If the ionization energy is low, that electron is cheap, it's easy to take. If the ionization energy is high, it's a luxury item. It's going to be very, very difficult to afford.
And as you can probably guess, this price tag is set by the atom size. Let's picture one of those huge atoms, way down in the bottom left corner, like francium. It is enormous. Its outermost electron is so far away from the nucleus, it practically needs a map to find its way home. And it's being shielded by a whole cloud of inner electrons. The nucleus has a very weak grip on it. It's incredibly easy to steal from. So it has a very low ionization energy. That electron is on the clearance rack. Now let's picture a tiny atom, like fluorine, in the top right. It's small, it's compact, its outer electrons are right up close and personal with a very powerful nucleus. That nucleus holds those electrons in a death grip. Trying to steal one is going to cost you a fortune in energy. So it has a very high ionization energy. The trend is the exact opposite of atomic size. It gets higher as you go up and to the right.
Okay, so that's the energy it costs to take an electron. Now let's flip it around. Let's talk about how much an atom wants to attract electrons in the first place. This is called electronegativity. It's essentially a measurement of an atom's greed for electrons when it's bonded to another atom. We measure it on a simple scale, usually up to 4. An atom with a high electronegativity desperately wants to pull bonding electrons towards itself. The undisputed champion, the greediest element of all, is fluorine, which clocks in at a whopping 3.98. It just really wants electrons.
So which atoms are going to be the best at attracting electrons from their neighbors? You guessed it, the small ones. It all comes back to size. In a small atom, that powerful positive nucleus is right near the surface. It's not buried deep beneath layers and layers of shielding. So when another atom comes nearby, the nucleus can exert a massive pull on that atom's electrons. It's like having a super strong magnet right up close. That's why the most electronegative elements are found in the top right of the table, the exact same corner where the atoms are the smallest and the ionization energy is the highest. It all connects.
And now we see how all these concepts lead to something you're probably very familiar with, the difference between metals and nonmetals. What does it actually mean for something to be a metal, chemically speaking? It just means it loses its electrons easily. Well, which atoms do that? The big ones with low ionization energy, down and to the left. That's your metallic character. And what's a nonmetal? It's an element that tends to gain electrons. Which atoms are best at that? The small, greedy, electronegative ones, up and to the right. So you see, the divide between metals and nonmetals on the periodic table isn't arbitrary at all. It's a direct consequence of these fundamental trends we've been talking about.
All right, so we've laid out the main highways on our map. We know the general rules of the road, but any good map has weird landmarks and interesting detours, and that's where things get really fun. In chemistry, we call these the exceptions. And it's easy to think of them as just annoying facts you have to memorize, but that's the wrong way to look at them. These exceptions are not mistakes in the rules. They are clues that point to even deeper, more subtle physics going on under the hood.
Let's look at a few famous rule breakers. First up, the size of gallium. It sits right below aluminum, so it should be bigger, but it's not. Gallium's actually a tiny bit smaller than aluminum. What's going on? Well, between them on the table, you have the 10 transition metals, and this is the first time we fill up the 3d electron subshell. And it turns out, d electrons are awful at shielding. They're just terrible bodyguards. So gallium's nucleus pulls its electrons in way more tightly than expected, causing this unexpected shrinkage. Next up, nitrogen versus oxygen. Oxygen is to the right, so it should have a higher ionization energy, but it doesn't. Nitrogen's is higher. The reason is all about stability. Nitrogen's outer subshell is exactly half full, which is a very stable, balanced state. Oxygen has one extra electron, which is forced to pair up in an orbital with another electron. These two negative electrons repel each other, which makes that electron just a little bit easier to remove. And finally, electron affinity, which is a measure of the energy change when an atom gains an electron. You'd think fluorine would be the best, but chlorine, right below it, actually has a slightly higher affinity. Why? Fluorine is just so tiny and its electrons are packed in so tight. Trying to shove one more electron into that crowded space creates a lot of repulsion. It's a little less welcoming than the more spacious outer shell of chlorine.
Here's another really cool exception you find way down at the bottom of the table with the really heavy elements. It's called the inert pair effect.
Now, for elements like lead or thallium, you'd expect them to lose all their outer electrons when they bond. But for these huge atoms, the two outermost electrons in the s orbital get weirdly stable. They become lazy. They just don't want to get involved in the chemical reaction. They form an inert pair. This means that these elements are often much more stable, losing two fewer electrons than you'd expect. It's why lead is very commonly found in a +2 charge state, even though it's in a group that suggests it should be +4. It's all because of those two lazy s electrons.
Now, this is one of the most elegant and curious patterns on the entire map: diagonal relationships. It turns out that some elements that are diagonal to each other, like lithium and magnesium or beryllium and aluminum, have weirdly similar chemical properties. How is this possible? Well, think about the two main trends. As you move one step to the right, atoms get smaller and more electronegative. As you move one step down, they get bigger and less electronegative. So what happens if you do both at the same time? The two effects can almost perfectly cancel each other out. The result is that you end up with an element that has a very similar size and electronegativity to the one you started with, leading to very similar chemistry. It's a beautiful example of how these competing forces balance each other out in unexpected ways.
So let's bring it all home. We've journeyed through the main trends. We've explored some of the fascinating exceptions and weird backroads on our map. It's time to zoom out and look at the grand picture that all of this paints. Because these aren't just a collection of separate rules. They are all deeply interconnected parts of one single, beautiful story.
So if there's one thing you take away from all of this, let it be this. Everything comes back to that simple tug-of-war we started with. The inward pull of the protons in the nucleus, and the outward push from the shielding of the inner electrons. That simple battle dictates an atom's size. That size dictates how tightly it holds its electrons, and how badly it wants more. And those properties, in turn, dictate its entire chemical personality. If it's a metal, if it's a non-metal, how it bonds, how it reacts. It really is that elegant. Two forces, one map, and from that, the entire infinite world of chemistry unfolds. Once you understand that core principle, you're not memorizing facts anymore. You're reading the map.
So, we've given you the legend, we've given you the compass. You now have the tools to navigate the periodic table. You can look at any element, see its location, and make a really good prediction about how it's going to behave, what its personality is like. You understand the language of the elements. So the only question left to ask is a simple one. Now that you can read the map, where are you going to explore next?